Now, there's several reasons why two waves could wind up colliding. One of the ways is due to reflection. So we're going to take a look at the reflection of waves, and then once we understand how they reflect, we'll take a look at what happens when these waves interfere with one another. So the first thing to understand is that anytime a wave hits a boundary, so down below, let's assume this is maybe an ocean wave hitting like a concrete pier. Anytime a wave hits a boundary, so it's going from traveling, in the air to hitting this solid structure, some of the energy will be reflected and be sent back the other way, and some will be transmitted. Some of that kinetic energy will actually be transmitted into the molecules in this concrete barricade, and that will continue on forward. So we're going to concern ourselves with the reflected portion, and the way that waves reflect depends on the classification of the boundary that it hits. And we generally classify these into two categories: the fixed boundary and the free boundary. So a fixed boundary is just a boundary that's not movable. It's fixed in place. And a free boundary is a boundary that's free to oscillate. It's free to kind of move up and down or side to side. It's easier, I think, to visualize it. So a fixed boundary would be like if you took a rope and you tied it to a pole. Anytime you sent the wave down and that wave hit that knot, it can't slide up and down the pole. That's fixed in place, so we're going to get a certain type of reflection. For a free boundary, that would be like if instead of tying it directly to the pole, I tied it to a ring, slid the ring over the top of the bar. Then anytime I sent a wave down and it hit that ring is free to slide up and down. So we say it's a free boundary that can actually move up and down. We can generally classify any type of boundary that a wave reflects off of as either fixed or free. Once we've done so, we can start to move towards understanding how wave interference or what type of wave interference is going to occur. So the important thing to understand is, imagine in both cases we send a wave down, one towards a fixed end and one towards a free end. Well, when it hits that fixed end, because it doesn't have the ability to move up and down, that wave is actually going to flip around on the other side, and the reflected wave is going to, in this case, travel back on the bottom or underneath that equilibrium point. A free boundary, because it can move up and down, well, that's really no different than if someone took their hand and moved it up and down, and that's going to send the wave or the reflected wave back on the same side. So the one thing we need to understand is that a fixed boundary reflects the wave on the opposite side that it came in on, and a free boundary sends it back on the exact same side. And that becomes important because if two waves are on the same side when they collide, we're going to have a different outcome than if the waves are on opposite sides. So we kind of just have to memorize this, but a fixed boundary reflects the wave on the opposite side, and a free boundary reflects the wave on the same side. All right, so now that we know how these waves could be coming back and which side they may be on, now we can look at wave interference. So when those two waves in those previous examples collide, we have to first realize they don't bounce off one another. They pass through one another. Waves are just energy, right? You're not transporting matter. You're not transporting mass with these waves. You're transporting energy. And energy can just pass through each other, or the wave energy can pass through. It's not going to bounce off because you don't have physical molecules that are trying to occupy the same space, which is what happens when things bounce off of one another. Two objects are trying to occupy the same space. But this is energy. Energy can occupy the same space as other energy, so they pass through one another. And we call this wave interference. So here we have the two cases we looked at in the previous example. In the first case, we have waves where the amplitudes are on the same side and they're going to collide. And on the bottom case, we have waves with amplitudes on opposite sides. So what we just need to recognize is that in the top case, when those two waves collide, those amplitudes will combine for a split second, and then those will pass through one another. But for the brief moment where they share the same space, you will have double the amplitude. And in the case on the bottom, you'll have no amplitude because the wave that's on the left initially is going to try and pull that rope upwards, but the wave on the bottom is going to try and pull it downwards. It's actually going to cancel out. We call these two types of interference constructive interference for the top case, constructive because you add the amplitudes together. And in the bottom case, we call it destructive interference because you subtract those amplitudes. So with constructive interference, we go from two smaller waves to one larger wave. And in destructive, it's the opposite. We go from two smaller waves, but on opposite sides, to essentially, for a brief moment, no wave, because that energy kind of cancels out for a brief moment. But then those waves will continue to travel as if they never interfered. All right, so make sure you understand constructive interference and the fact that we add the amplitudes. Destructive interference, we subtract the amplitudes. And in the next video, we'll take a look at some examples, and we'll see how we can use this simple addition and subtraction method to figure out what the interfered wave pattern will look like.